Chapter 2 begins on page 10, and it's a picture of a gigantic, beautiful red flower. And then on page 11, it says Chapter 2 and measurement. So you know that this chapter is all about measurement. Let's read together the verse from Wisdom on page 11. But you have disposed all things by measure and by number and weight. For with you great strength abides always. Who can resist the might of your arm? Indeed, before you the whole universe is as a grain from a balance, or a drop of morning dew come down upon the earth. And how could a thing remain unless you willed it, or be preserved, had it not been called forth by you? But you spare all things, because they are yours, O Lord and lover of souls, for your imperishable spirit is in all things. Turn to page 12, please. The first thing we're going to do is look through our chapter so we get a basic idea of what the chapter is about. So we're going to look at the major headings and the unit headings, okay? On page 12 in black, it says measurement. Underneath that in yellow, it says the metric system. Turn to page 14. In the middle of 14 in yellow is written mass. On 15, it says area in centimeters squared and volume in centimeters cubed and cc. Turn to page 16, and then you have some dark headings in black. It says area equals length times width, volume equals length times width times height. And on 17, there's a heading called liquid volume, that's in yellow, temperature in yellow, and heat in calories in yellow. And that's it for the whole chapter. It's a short chapter, and so we're going to be learning about the basic units of measurement for volume and length and temperature. Okay? Let's read together on page 12. Remember to sit up in a good position for learning and follow along with the words with your eyes, and if you can do so, follow along with your finger as well. Let's read together on page 12. The metric system. You are probably used to using units of measurement such as feet, cups, and pounds in your everyday life. Now you will learn the skill of using the metric system, a way of measuring objects based on the number 10. The metric system is used by industries and scientists throughout the world because it is easier to convert measurements into other units in the metric system than in other systems. Learning to use the metric system is an important and necessary preparation for advanced science studies. To measure the length of an object like yourself, use a meter stick. You are probably taller than 1 meter stick, but not as tall as 2. As a matter of fact, Average Adam, your all-American everyday boy of 12 years old, top of page 13, is exactly 1.5 meter sticks tall. His cousin, Haphazard Harriet, is actually a little taller than Adam now, but won't be in a few years. That's just telling us in kind of a funny way that on average 12-year-old girls are taller than 12-year-old boys, but then in a couple of years the boys will become taller than the girls. Let's continue reading. The basic unit of measurement for distance is meter. The instrument used for measuring distance is the meter stick. A smaller instrument is the centimeter ruler. Notice that a meter is divided into 10 parts called decimeters, into 100 parts called centimeters, and into 1,000 parts named millimeters. And then did you notice in the parentheses the abbreviations for those? DM is decimeter, cm is centimeter, and mm is millimeter, and all of those are in lowercase letters. Meters, centimeters, and millimeters are all units of measurement. Look up unit in the glossary to make sure that you know its meaning. More importantly, be sure to include units with every measurement you write down. Middle of the page on 13. There is one problem with the meter. Sometimes it takes hundreds of them to measure a distance, and sometimes it takes only a tiny, tiny fraction of a meter to measure an organism. Pauline Musters, the smallest woman on record, was only 0.59 meters tall at 18 years old. But Even that is big when compared to a Bacillus bacterium that is only 0.000001 meters long. Having to write 0.000001 meters is a bit of a pain in the neck. As a result, the metric system has units that are based on the meter, but are bigger or smaller. It is more convenient to say 1 micrometer, which is 1 mu and m, for the size of a bacillus, and it is much easier to write as well. Mu is the Greek letter mu. It's pronounced mu like the sound a cat makes. Since the metric system is based on 10, you can change units simply by moving the decimal point. You can use the metric prefixes chart, and that's at the top of page 13, to convert one unit to another. For example, average atom is 1.5 meters tall, but how many centimeters tall is atom? Find the basic unit on the chart, that's meters, then count the number of steps you must move to get to centimeters. So if you go up to the top of the page and you find meters, that's in the very center, and then you move how many spaces to get to centi? It's 2 spaces to the right. So now you move your decimal point 2 places to the right. So remember, it was 1.5 meters first, and now you move the decimal point 2 places, and now you're at 150 centimeters. Turn to page 14, please, up at the top of the page. Now, write this number with the correct units as your answer. Average atom is 150 centimeters tall. Pauline Muster was 0.59 meters tall. How many centimeters is this? So remember, you just move the decimal point 2 points to the right, so it would be 59 centimeters tall. Let's continue reading. You must know the correct abbreviations for different units. The centimeter, lowercase cm, is approximately as wide as the average pinky finger. Centimeters are used to measure hand-sized things. Kilometers or kilometers, that's written lowercase km, are used to measure distances between cities. Micrometers, and that is listed as a mu and a m in lowercase, also called microns, are used to measure microscopic objects. You already know the basic unit of length is the meter, but what are the units for liquid volume and mass? Soda bottles come in 1 or 2 liter sizes, and candy bars are often measured in grams. So in the middle of page 14 in yellow, let's talk about mass in grams. The triple beam balance is used to measure mass in the unit grams. Do not confuse mass with weight. Mass is the amount of matter present. Weight is a measure of the force of gravity on an object. 1,000 grams equals 1 kilogram, which is approximately 2.2 pounds on Earth. The kilogram is approximately the mass of 7 baseballs. Notice that the metric system uses the same prefixes even when we are measuring mass instead of distance. Just as 1,000 meters equals 1 kilometer, so 1,000 grams equals 1 kilogram. The basic unit is different, but the prefixes are the same. Turn to page 15, please, up at the top of the page. Robert Wadlow, the tallest man on record, was 7 feet 1 3/4 inches tall when he was 13 years old. At that time, his mass was 115,666.05 grams, which certainly sounds like a lot. But the gram is approximately the mass of 1 medium-sized paperclip. A better unit for Robert's mass would be kilograms. Use the metric prefixes chart to figure out Robert's mass in kilograms. Start at the basic unit, grams, and count the steps to kilograms. Since you moved 3 places to the left on the metric prefixes chart, you should move the decimal 3 places to the left. 1 place, 2 place, 3 places. This is the magnitude of your answer. So it's going to be 115.66605 kilograms. Round off this number to a reasonable number of places and add the correct units for your final answer. The 13-year-old Robert Wadlow had a mass of approximately 115.7 kilograms. For comparison, the average 12-year-old girl's mass is about 39.7 kilograms, and average Adam would be roughly 1.45 kilograms less than that. As big as Robert Wadlow was, it would take over 1,200 13-year-old Robert Wadlows to have a mass equal to one blue whale. What is the mass of this blue whale in megagrams? We're in the middle of 15. You really must remember the metric prefixes in order with the blank spaces included. The prefixes used for values greater than 1 are Greek. That's mega, and then blank space, kilo, hecto, and deca. Latin prefixes indicate values less than 1, such as deci, centi, milli, and then a space, and then there's micro. All of the prefixes are based on the number 10. At the bottom of 15, let's read about area in centimeters squared and volume in centimeters cubed and cubic centimeters. That's in yellow. Wow, 510,700,000. Is that big? Is that big? Measurements must always include units. If the above is in square millimeters, that's mm with a little 2 above it, then it is only 510 square meters, just 2/3 the area of a baseball field. But when we write 510,700,000 with the units being square kilometers, now that is big. The surface area of the entire Earth is approximately 510,700,000 square kilometers. To compare, average Arnold, that is average Adam's average-sized dad, has a skin surface area of about 186 meters squared. That's a surface area of 0.0000186 kilometers squared. Let's try to see the basic idea of area. Use a centimeter ruler to measure the rectangle in figure 2.6. By the way, that is on page 16. The rectangle is 2 centimeters on one side and 3 centimeters on the other. If we mark off small squares that measure 1 centimeter, turn to page 16, we find that 6 of these little square centimeters will fit on the 2 centimeter by 3 centimeter rectangle. The unit cm times cm is called square centimeters, and it's written lowercase cm with a tiny raised 2 after the m. You must memorize the general formula for rectangular area, which is area equals length times width. Do you see that at the top of page 16 written in bold capital letters? When doing an area calculation, always write the formula, then subtract the numbers with their units, and finally box your answer with the correct units. So let's do an example based on the figure 2.6 on the top left of page 216, of page 16, not 216. Area equals length times width. The area is 3 centimeters times 2 centimeters. And so the area, 3 times 2 is 6, so the area is 6 centimeters squared. Whenever additions or subtractions are done with units, the units must be the same. For area or volume problems, the units must also be the same as well. For example, look at the figure 2.7 in the middle of the page 16. It's a multicolored cube. Look at the writing on there. On the vertical side, it says 3.0 centimeters. Then on the horizontal line on the bottom, it says 40.0 millimeters. And then on the other side, that's kind of diagonal, it's written as 0.20 decimeters. So we've got centimeters, decimeters, and millimeters all in one figure. So in order to figure out the area, we have to put them all in the same unit. And so we're going to convert all of those units to centimeters so that the answer makes sense. So here we go. Let's take care of that. Let's see. It says almost everyone knows that the formula for area is length times width, but we must change centimeters or millimeters before we multiply. Note that the answer here is written in square centimeters. So let's find the area of the front of that box. Area equals length times width. Well, the length is written as 40.0 millimeters, and the width is labeled as 3.0 centimeters. So we need to put those in the same units. So to convert that from millimeters to centimeters, we have the area equals 4.0 centimeters times 3.0 centimeters. 4 times 3 is 12, so our area is 12.0 centimeters squared. At the bottom of 16, this same idea that units must be the same also applies to rectangular volume calculations. So volume, keep in mind, you have to memorize this. Volume is length times width times height. So if you're ever dealing with volume, length times width times height, and you find that your units are different, like millimeters, centimeters, and decimeters, you have to convert them all to the same unit. You choose which unit makes most sense, convert them to the same unit, and then you multiply. Okay, so they wrote out the problem down at the bottom of 16. Volume equals length times width times height. Volume equals 40.0 millimeters times 3.0 centimeters times 0.20 decimeters. They converted all of those to centimeters and then they rewrote the problem, and this is how it's rewritten. Volume equals 4.0 centimeters times 3.0 centimeters times 2.0 centimeters. And the final answer is volume equals 24 centimeters squared. Okay, on page 17, we're on the last page of the chapter. Read up at the top. Note the units in the answer. Metric volume is measured in cubic centimeters, abbreviated lowercase cm with a tiny raised 3. It can also be cc, and cc stands for cubic centimeters. It means the same thing. cm3 or cc means the same thing. You may have seen a baby bottle marked in cubic centimeters or a motorcycle that is 80 cc's. The cubic centimeters marked on the bottle measure the volume of liquid it can hold. The cubic centimeters on the motorcycle measure the volume of its cylinder. The more cubic centimeters, the bigger the piston, and thus the more power. On 17 in yellow is liquid volume, measured in liters, which is lowercase l. Liquid volume is measured in liters. The milliliter is approximately 8 drops of water. When you memorize the volume formula, you must also remember this fact. 1 milliliter equals 1 cubic centimeter. 1 ml equals 1 cc. So we could say that a 2-liter soda bottle is 2,000 mLs. That is the same as 2,000 cc's, or cubic centimeters. Let's read temperature on page 17 in yellow. Temperature. In the metric system, temperature is measured in centigrade degrees, or that's listed as a little tiny temperature degree mark and a capital C. Centigrade refers to the 100 graduations or degrees from freezing to boiling. This temperature scale is also called Celsius, after its inventor, Andre Celsius. Temperature is how cold or hot something is compared with a standard. Room temperature is about 20 degrees centigrade or Celsius, and the human body temperature is 36.5 degrees centigrade or Celsius. Each measurement of temperature must include the correct units. You may be familiar with Fahrenheit degrees. That's labeled as a degree symbol and a capital F, which are used in our weather reports. In chemistry and physics courses, you will be using the absolute scale measured in kelvins, labeled with a capital K. The fixed points for water are its freezing point and boiling point. Pure water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, and 273 kelvins. At 1 atmosphere of pressure, pure water boils at 100 degrees Celsius, 212 degrees Fahrenheit, and 373 kelvins. So here's a question. Which is colder, 0 degrees Celsius or 32 degrees Fahrenheit or 273 kelvins? That's a trick question. They are all the same. None of them are colder. They are all the same temperature, just the units changed. You can measure temperature in 3 different units. All right, the very last part of Chapter 17 is at the bottom, or Chapter 2 is at the bottom of 17, heat in calories. A calorimeter is used to measure heat in the unit calories. Try not to confuse temperature with heat. Temperature is how hot or cold something is compared to a standard. Heat is a measure of the amount of energy available for transfer to another object. That is, heat is the measure of the kinetic energy of the molecules in an object. We're done with the chapter, but I just wanted to point out briefly, on page 17, underneath the picture of the thermometer, there's a little thing in yellow. It says worksheets, diagram, and microscope. Always be on the lookout for those in your textbook because it tells you what workbook pages you can fill out based on the information found on these 2 sheets that are open in your workbook or in your textbook at the time. That's it for Chapter 2. Bye-bye.